Good morning. In Fana flow, so far we have derived differential term relations from fundamental equations. Now, let us recall those derived differential term equations one by one. First, from state equation, we have a relation between pressure, density and temperature. We denoted this equation as number 1, and then from continuity equation, we have relation between density and velocity as d rho by rho is equal to minus 1 by 2 d of v square divided by v square. So, we denoted this equation as number 2, and then we derived a new momentum equation especially for this case. So, from that relation, then from momentum equation, we have a relation between pressure, Mach number, velocity, pipe wall friction and element length dx. So, dp by p is equal to dp by p plus gamma m square divided by 2 into d of v square divided by v square plus gamma m square divided by 2 into 4f dx divided by d is equal to 0. So, this is equation number 3. So, then from energy equation, we have the relation between temperature, Mach number and velocity is dt by t plus gamma minus 1 by 2 into m square into d of v square divided by v square is equal to 0. This is equation number 4. Then finally, we have a relation from Mach number relation. Similar to the above equation, it also relates temperature, Mach number and velocity. Equation. So, we have a relation d of m square divided by m square is equal to d of v square divided by v square minus dt by t is equal to 0. So, this is equation number 5. So, if you look at these two relations, both relates temperature, Mach number and velocity. Now, we can represent one term variation as a function of another term using these two equations. To get to represent velocity variation as a function of Mach number variation, let us substitute this equation number 4 in equation number 5. Substitute equation number 4 in equation number 5 to represent velocity variation as a function of Mach number variation. So, d of m square divided by m square is equal to d of v square divided by v square minus dt by t. So, minus of dt by t is equal to this term, positive this term, that is gamma minus 1 by 2 m squared into d of v square divided by v square. So, in these two terms we have a common term d of v square divided by v square, take that outside. So, remaining term will be 1 plus gamma minus 1 by 2 m square. So, d of m square divided by m squared is equal to this term, but our objective is we have to represent this velocity variation as a function of Mach number variation. So, d of v square divided by v squared is equal to 1 divided by 1 plus gamma minus 1 by 2 m square into d of m square divided by m square. So, let us say this is equation number 6. Now, either we can use this relation or this relation to represent dt by t as a function of Mach number variation. We know the value of this variation in terms of Mach number variation. So, finally, we will get dt by t as a variation of Mach number. So, again I am going to use the one of the equations, let us say from equation number 4 can represent dt by t after simplification. This will be equal to minus gamma minus 1 by 2 into 1 plus gamma minus 1 by 2 m square into dm square. So, now this temperature variation also represented as a function of Mach number variation. Let us say this is equation number 7. Then from this equation, from equation number 2, we can represent d rho by rho as a function of Mach number variation from this relation. So, d rho by rho is equal to minus 1 by 2 d of v square divided by v square. This is equal to minus of 1 by 2 into this whole term, is 1 plus gamma minus 1 by 2 m square into d of m square divided by m square. So, this is equation number 8. Then, so in this relation, now we know this variation as a function of Mach number variation, also this variation as a function of Mach number variation. So, finally, we can represent this pressure variation, static pressure variation as a function of Mach number variation. So, now we are going to use equation number 1. So, then from equation number 1, so dP by P is equal to this term plus this term. So, after simplification I will get dP by P as minus 1 plus gamma minus 1 m square divided by 2 into 1 plus gamma minus 1 by 2 m square into d of m square divided by m square. Let us say this is equation number 9. So, as of now we have represented only static property variations as a function of Mach number variations. Then we need to get a relations for stagnation properties. So, when you look at stagnation properties, we know that the flow process is an adiabatic process. So, in an adiabatic process, stagnation temperature, stagnation enthalpy and stagnation specific internal energy will be constant. So, we do not want to worry about these stagnation properties. The only property remaining is stagnation pressure. So, for that we are going to use stagnation isentropic relation. So, then from stagnation isentropic relation, so that is P naught by P is equal to 1 plus gamma minus 1 by 2 m squared into gamma by gamma minus 1. So, this equation we have to convert into differential terms. So, for that I am going to take logarithmic. So, P naught is equal to P into 1 plus gamma minus 1 by 2 m squared into gamma by gamma minus 1. Now, let us take logarithmic on both the sides. So, ln of P naught is equal to ln of P into P plus ln of this term. So, 1 plus gamma minus 1 by 2 m square whole power gamma by gamma minus 1. So, again we can rewrite this equation as ln of P into this power will come at the front, it is gamma by gamma minus 1 into ln of 1 plus gamma minus 1 by 2 m square. Now, we can easily differentiate this equation in terms of fractions, that is d P naught divided by P naught is equal to d of P divided by P plus gamma by gamma minus 1 into d of this term, and it will be 2 m square divided by the same term 1 plus gamma minus 1 by 2 m square. So, this is equal to dp divided by p plus gamma by gamma minus 1 into, if you differentiate the, we will get gamma minus 1 by 2 into d of m square divided by 1 plus gamma minus 1 by 2 m square. These two will get cancelled. This is equal to, so after simplification we will get dp naught by p naught as, after substituting this p naught as a function of Mach number variation, we will get this term as minus 1 minus m square divided by 2 into 1 plus gamma minus 1 by 2 m squared into d of m square divided by m square. Let us say this is equation number. Then from momentum equation we can represent that Mach number variation as a function of frictional coefficient and element length dx. So, now from momentum equation we can represent this term 4f dx by d as a function of Mach number variation, so gamma m square 1 plus gamma minus 1 by 2 m square into d of m square divided by m square. In reverse, here we can represent Mach number variation as a function of this frictional coefficient dx in reverse. So, this d of m square divided by m squared is equal to the reciprocal of this term gamma m square into 1 plus gamma minus 1 by 2 m square divided by 1 minus m square into 4f dx divided by d. Actually, all the property variations are only function of this dx value and f value. So, now we can represent all the flow properties variation as a function of dx. So, now rewrite everything in terms of dx. Now, we will rewrite everything in terms of dx. So, dx. So, of d into v square divided by v square is equal to dv by v equal to gamma of m square divided by 2 into 1 minus m square into 4 of dx divided by d. Then d rho by rho is equal to minus gamma m square divided by 2 into 1 minus m square into 4 of dx divided by d. Then dt by t is equal to, is a function of dx, it is gamma by gamma minus 1 m square divided by 2 into 1 minus m square into 4 of dx by d. Then dp by p is equal to minus gamma m square 1 plus gamma minus 1 m square divided by 2 into 1 minus m square into 4 of dx divided by d. And also we have p naught variation relation. So, that is also to be represented as a function of dx variation is 4 of dx divided by d. Now, so all these four properties variations are as a function of dx and f. Using all these relations, if we plot a graph between enthalpy and entropy, we will get a graph like this. Specific enthalpy in y axis and entropy in s axis. So, if we plot the flow properties variation, so we will get a curve like this. So, in this curve, this point denotes sonic condition, and this curve, the curve above this sonic condition denotes the subsonic flow, and the curve below the sonic condition denotes the supersonic flow. We know that from Newton's second law, in an adiabatic process, entropy always increases. That means, so here the flow direction should be towards sonic condition, and here also the flow direction must be towards sonic condition. See, here the hidden meaning is, for a subsonic inlet condition, the effect of friction always accelerates the flow towards the sonic condition for a particular length. So, beyond that length, that flow condition will remain as a sonic condition. Similarly, for a supersonic flow condition, inlet condition, the effect of friction decelerates the flow for a particular length of the pipe. It will reach sonic condition. Beyond that duct length, that flow will remain as sonic condition. Now, let us consider two state point either in subsonic flow condition or supersonic flow condition. So, I am going to consider here in subsonic flow condition, here one state point and here one state point. Now, I am going to integrate whatever the equations I got so far to this flow properties at state point 1 and state point 2. So, if we do that, we will get the relation in integral form between state point 1 and state point 2. So, those relations are V 2 by V 1 is equal to m 2 by m 1. This is applicable for this subsonic flow region as well as in supersonic flow region, into 1 plus gamma minus 1 by 2 m 1 square divided by 1 plus gamma minus 1 by 2 m 2 square whole power 1 by 2. Then rho 2 by rho 1 is equal to V 1 by V 2. Then T 2 by T 1 is equal to 1 plus gamma minus 1 by 2 m 1 square divided by 1 plus gamma minus 1 by 2 m 2 square. Then P 2 by P 1 is equal to m 1 divided by m 2 into 1 plus gamma minus 1 by 2 m 1 square divided by 1 plus gamma minus 1 by 2 m 2 square whole power 1 by 2. Then stagnation pressure relation, P 02 divided by P 01 is equal to m 1 divided by m 2 into 1 plus gamma minus 1 by 2 m 2 square divided by 1 plus gamma minus 1 by 2 m 1 square whole power gamma plus 1 divided by 2 into gamma minus 1. Then we can represent the entropy variation S2 minus S1 divided by R as equal to minus of ln P02 divided by P01, since the flow is an adiabatic flow. Then we can also represent 4f, the duct length, divided by D as a function of m1 and m2, m2 square minus m1 square divided by gamma into m1 square m2 square plus gamma plus 1 divided by 2 gamma ln of m1 square divided by m2 square into 1 plus gamma minus 1 by 2 m2 square divided by 1 plus gamma minus 1 by 2 m1 square. So, now we represented flow properties at state point 1 and state point 2. So, all are as a function of inlet Mach number and exit Mach number for a duct length of L. Now, we are going to compare a state point to sonic condition. The same relation we have to modify to sonic condition, exit as a sonic condition. So, for a inlet condition, the flow properties variation between for a inlet condition and sonic condition. For particular inlet condition and sonic condition. For particular inlet condition and sonic condition, which means V1 will be V, V2 will be V star. That is, at this point Mach number is equal to 1, velocity will be equal to speed of sound. So, V2 will be equal to A. So, this is denoted by star. So, now we are going to substitute this terminologies m into gamma plus 1 divided by 2 into 1 plus gamma minus 1 by 2 m square whole power 1 by 2, then rho by rho star is equal to V star by V, T by T star is equal to gamma plus 1 divided by 2 into 1 plus gamma minus 1 by 2 m square, then P by P star is equal to 1 by m into gamma plus 1 divided by 2 into 1 plus gamma minus 1 by 2 m square whole power 1 by 2, then stagnation pressure ratio, this is equal to 1 by m 2 into 1 plus gamma minus 1 by 2 m square divided by gamma plus 1 into gamma plus 1 divided by 2 into gamma minus 1, then S star minus S divided by R, this is equal to minus ln of P naught star divided by P naught. Then this relation, in this relation we have to substitute M2 as 1 and M1 as M, then this 4f L maximum, the duct length required to achieve this sonic condition for a particular inlet condition. This is equal divided by D is equal to 1 minus m square divided by gamma m square plus gamma plus 1 divided by 2 gamma into ln of gamma plus 1 into m square divided by 2 into 1 plus gamma minus 1 by 2 m square. So, after referring this equation for an Mach number m1 and m2, we can represent this term as a function of 4f L maximum divided by D for a particular state point 1 Mach number and state point 2 Mach number, inlet Mach number and exit Mach number. So, that is represented as 4f L divided by D is equal to 4f L maximum divided by D of Mach number 1 minus 4f L maximum divided by D of Mach number 2. So, inlet Mach number, this value for inlet Mach number minus this value for exit Mach number will give us this value, that duct length value. So, this is a very important formula. So, at last now we are going to represent flow properties variation for supersonic inlet and subsonic inlet flow. So, here the inlet Mach number will be more than 1, that is M1 Mach number will be more than 1, here the M1 Mach number will be less than 1. See, if you consider Mach number, so in fan off flow the effect of friction increases this Mach number, in supersonic inlet flow this is the effect of friction decreases the Mach number, here the Mach number will be increased. Here if you consider velocity, so here the velocity will decrease, here the velocity will increase. For pressure, if velocity decreases, obviously pressure will increase, here it will decrease. Then if you look at density, so density also increases here, similar to static pressure, this will decrease here. Then temperature, so here temperature will increase, So, from state relation we can easily represent these three. It increases, this one is decreases, then P naught value decreases for both the cases, then T naught, since the flow is an adiabatic flow, this T naught will be constant at all the point. Then entropy, if we compare entropy, here also it increases, here also it increases. That is all for today's class. Thank you.